Portable speaker. A wonderful device that can fill any event with mood. Whether it's a picnic or just some weird suspicious outdoor activities, rest assured, it'll be more fun with a speaker. And somehow, I don't have one. It's time to fix that. I'm going to build not just working speaker, but a fine device that I can use on my day purposes, and do it from scratch. This will not be an easy job, involving many stages, from designing internal circuits to the final shape. I will try to describe the process as best as possible. Let's get started. The first thing I need to do is determine what specific features my device should have. First of all, it is an audio device, so it definitely needs a speaker. Next, we need something that will play music on it. My music will be digital, so it needs a processor. As a music source, I'm going to use my smartphone or any other device, so we'll need a Bluetooth module. Also, I want the device to be portable, so it will need a built-in rechargeable battery. It is better to start selecting components with choosing a processor. I'll explain why. You can imagine a processor as a conductor in the world of electronic components. It can receive, process and transmit signals, controlling the entire ensemble of devices. The rules by which the processor works with these signals are described by developers and placed in the firmware, the executable code that is loaded into the device's memory. A small chip can control both the simplest toy and large serious equipment, but different tasks require different functions, and it is important to choose a processor that will combine all the components, modules and characteristics necessary for the task. This is the very heart of your device. The best option for my case would be the ESP32 chip. It satisfies several of my needs at once. It can work with Bluetooth, has enough space to accommodate libraries for music processing, consumes little energy and is very compact. The chip itself requires 3.3 volts to operate. But it also can handle with 5 volts because of internal step-down. There is USB Type-C on board, which can be used for power supply. Also, you can supply 5 volts directly by wiring VIN input. Or just directly connect 3.3 volts to the corresponding pin. These are the only 3 ways to power the processor, so we should choose the one that suits our design. So we have the right chip, but how do we tell it what to do? I'll explain it, briefly. Processors don't understand our language. They can only understand specific instructions, which are large strings of zeros and ones. It's called machine language. But we can't use it to describe our tasks to the device. For this, we invented different programming languages that a human can understand. When our understandable code with instructions is written, it should be compiled. Compilation is basically translation to machine language. Once we have instructions that are understandable to the device, they need to be uploaded into its memory. We also have different software to perform both tasks. It is called IDE, which, in my case, will be Arduino. I'm not going to explain how to code, that's too much of a topic, and that's not what the video is about. But I will leave a link in the description to library that I used for this project. It's well documented and quite simple. To transmit digital audio between integrated circuit components, the I2S protocol is used, which is well described in Wikipedia. It uses 3 data transmission channels. Serial clock line, which represents sample rates. Word select line, responsible for sound channel to provide stereo. And serial data line, audio data itself. So, I connected the chip to the computer and loaded it with all the necessary instructions. Now it can receive audio streams from devices via Bluetooth, as well as transmit the received data to its pins. For testing, I will use a breadboard, which is very convenient for prototyping. As you can see, I have 5 wires coming out of the chip. 2 of them are for power supply. The red one is connected to the 3.3 volt pin and the black one is connected to ground. The rest is our 3 channels of I2S digital audio protocol. Earlier, I specified which pins my chip should broadcast audio data to. And here they are. In order to check whether our chip broadcasts music, it will be enough for us to use only one channel. the main one, containing the audio data. I'll connect small wire with tip to it, and another one to the ground. Of course, first we need to connect the chip to a power source. For now I will just use an USB port. Once the chip is loaded and we connected to it, it should broadcast all sounds from device. Now we can test our sound by touching the tips to the contacts of any small speaker. I took a pair of old headphones, and we'll just touch the jack with the tips. Let's try. The reason our music sounds like noise is because we only used one raw channel of digital audio. It is not intended to be used that way, and we did it just for test. To make our music sound good, we need to combine all three channels of the I2S protocol, and the next part of our circuit will help us with this. The amplifier. An amplifier, as the name suggests, is a circuit that amplifies the input value. They are used wherever sound is involved. Thanks to amplifiers, we can play our music on huge speakers at music concerts and sports stadiums. Of course, we will need it for our device too, because we want to hear a loud enough sound from a speaker that is much larger than headphones. And luckily for us, some amplifiers support I2S protocol as an input. This one will allow us to perform two tasks at once: converting digital sound to analog and also amplify it. Let's take a closer look. Amplifier should be powered, so it has VIN and ground inputs. This one can handle up to 5 volts. On the left side it has 3 inputs for digital sound: word select line, serial clock line, and serial data line. You can see that there are 2 more inputs on the board. The one marked as SD is the channel selection pin. It controls which channel, left or right, it should play. By default, the device outputs a channel mix of both. The other, labeled as gain, controls how much the input signal should be amplified. Finally, board has 2 outputs for speaker. I have already prepared another one by soldering the wires we'll need, so we can connect and test it. Let's go back to our breadboard. First, let's disconnect these wires. We won't need them yet. We have 5 pins on the board, and we're going to use 5 wires from the amplifier. 2 power wires, and 3 more for our digital audio lines. I'm just going to connect them one by one. That's it. To test the sound at the output, I'm going to use all the same wires with tips. I'll just push them through the holes. Hopefully, we will hear some music now. Well, that's a success. Our chip works, but it's still powered by a wire, which means it's time to design the power supply. The task seems simple at first glance, just choose a suitable battery and connect it to the chip. However, everything is a little more complicated since we want to make it rechargeable. The first thing you can notice on the batteries is this little strip. It is a battery protection module, which protects the battery against common dangers such as overcharge, over-discharge, short circuit, overcurrent, and temperature. This protection also exists on my other batteries, but it is not visible under the packaging. It is very important to make sure that the battery is connected through this module, otherwise the device will be dangerous to use. The correct way to charge a lithium-ion battery involves several different stages, each using a different current to ensure a quality charge. Luckily, we don't have to build the charger logic ourselves, because there are ready-made solutions. This is a very handy charging board. It comes with a large capacitor separately, which we will install and solder a little later. This board will allow us to control the charge and effectively use the device, both from the battery and from the wire during charging. Let's look closer. The board is used to control the charge of 3.7-volt batteries. Here are the contacts for the capacitor that I mentioned earlier. Charging can be done with different power sources. The board is compatible with a 6-volt solar panel, which we will not use in this project. These are the contacts for connecting it. And this is the place for our battery. Once it placed, board will provide battery power to the outputs. Here they are. Also, energy will be supplied here from any power source connected, even if there is no battery at all. Finally, on the right side there are contacts for our external power supply, which will charge the battery even while the device is in use. I'm going to use a separated USB socket to isolate our system from power while the device is off. So, I will need a small board with USB Type-C socket on it, which will be used for charging. Also, for more mobility and convenience during assembly, I will use a bunch of 2-pin 2.54mm connectors. Of course, to put it all together, I'll need some flux, solder paste, solder. Let's move forward in time and look at the result. Here it is, with all the necessary connectors and a capacitor installed. We definitely don't need such long capacitor legs, I'll cut them off later. Otherwise, our charger is completely ready for use. In fact, our board has easily become a full-fledged charger for 3.7-volt lithium-ion batteries. All that remains is to connect the battery. And we can still use it through the output pin. Let's test it. After connecting the battery, nothing will happen. Need to connect the USB cable. You can see two indicators lit up. One means that an external power source is connected, the second means that the battery is charging. It will automatically stop charging when the battery is full. If I disconnect the battery, there is only one indicator left. Nothing charges anymore, only external power source operating. Great, let's see what we have. So our core is an ESP32 chip, it has Bluetooth and can handle digital audio. Next, our power supply, it's 3.7-volt Li-ion battery, 6000 mAh. Battery connected through a charger, and the device can be powered by a cable if the battery is dead. Amplifier receives digital audio data from chip, converts it into analog sound, and push it to the speaker. But we still missing something in between out power source and chip. The part that will help us stabilize the voltage of our power supply. It is a step-up converter. The reason we need this is because our output voltage varies greatly from 3 to 5 volts, depending on the battery charge and the cable connected. And no matter what voltage we have on one side, step-up helps us to always have the same on the other. It's pretty simple, there are 2 inputs on one side and 2 outputs on other. It uses a variable resistor which can be adjusted to the desired voltage. The adjustment is made by tightening the bolt while measuring the output with a multimeter. In my case, I set it to 5 volts. Back to our scheme, now it looks functional. The only one last part that I want to add is a small power button right after the charger, so we can completely cut off power from our chip while still able to charge battery. This type of button is called a latching switch. It maintains its state once activated, and need another push for deactivation. I chose one with a LED inside, I will use it for power state indication. So, it looks like we have everything ready to deliver sound to the speaker. Let's take a look at it. I picked this one up from the local market because it has good reviews. It is a small 4-ohm speaker that can handle up to 3 watts. Perfect for our amplifier and has a diameter of only 40 millimeters. However, if we want the sound to be good, we will need a proper enclosure. And here we move on to the next part. Designing the device body. I started by creating rough models of my components to get an idea of how I could place them. And after that, I just moved and rotated them, keeping in mind that they should be connected to each other in series. By placing the components in their future positions, I gradually began to imagine the possible dimensions of the entire device. After a while, I created simple shape for body, and enclosure for speaker itself. I chose the sphere shape, because as I know, it is good to fight edge diffraction and sound quality will be better. At one point, I thought, why am I using one speaker? Why not make 2 and get the ability to play stereo sound? I liked this idea and started to reconsider the positioning. Also, I finally created exact models of all components in size. Since I have now decided to use 2 speakers, I will also need 2 amplifiers. After quite a while of arranging modules, thinking about the design and several iterations, I, finally, came up with this. Well, it was not an easy task to think through everything down to the smallest detail. The most interesting thing is of course inside. Let's go under the hood. First comes the base. This is the one piece that everything else will sit on. It's full of little details and thoughtful little touches. ESP board will be placed on very front. Behind the board, in the center of the device, located the heaviest element, the battery. Power control board, located at the rear of the device. As a charging input, we use a Type-C socket, which is sitting on the back wall. Directly above it is the power switch button. Next, to stabilize the voltage, we have a step-up board. It is located below our chip. And of course, 2 amplifiers. 1 per speaker, each on its own side. The amplifiers transmit sound to the speakers, which have their own, thick, spherical shell. The shells will be printed separately and secured to the base with screws. The front side of speakers will be covered with decorative mesh, which will also slightly focus the direction of the sound. On the bottom there is a place for small rubber pads. And finally, the case. Case should cover the whole thing after assembling. Since it's a single piece with nothing attached to it, its design can easily be modified later. It's time to print. The first piece we get is speaker enclosure. It was printed with thick walls and no cavities inside. The less the sound resonates with it, the better. Inside, in the center, you can see the edge of the support. It is needed for the backside, since it actually hangs in the air during printing. We don't need it anymore, and to take it out, I'll just break it off. What a beautiful tree! At the bottom, you can see 2 small holes. They are for the speaker wires and are made exactly to their size, so the wire will cover them itself. I know exactly where the components will be located, so I prepared a piece of wiring that should fit. At first glance, nothing is clear, but in fact, everything is extremely simple here. We have 2 amplifiers, which means that each data stream from chip must be duplicated. This also applies to the power supply. And here in the center, we just clone all our 5 connections, so both amplifiers can receive same data and energy. I also installed a power connector. All incoming power is distributed from here, through a step-up converter to the chip and to the amplifiers directly. We can't solder the speakers because we have to run the wire through an enclosure first. As you can see, the speaker fits perfectly. But it's too early to install it, a couple more things need to be done. In order to prevent sound waves from resonating inside as much as possible, I will put foam in there so that it covers the walls. After I have it nicely distributed inside, I will add something more. A piece of terry towel. And the last thing I want to do is add a little spacer between the metal and the plastic. Regular electrical tape strike should be enough. Finally, we are ready to install the speaker in place. All the screws are tightened, and I will cut off the excess tape with a knife. After I repeat the same process with the second speaker, this is what we got. You may have been wondering all this time, what are those yellow wires sticking out of your amplifiers? Well, yes, I didn't tell you about their purpose. When I was talking about the amplifier, I mentioned that one of its inputs is used to determine whether the speaker is right or left. With their help, we can make the speakers play only their side. But that's later, for now just don't pay attention to them. Let's move to the next part. It is the bass. Looks good, all the parts are in place. On the back side you can see another support, it is needed for the holes. Another tree for the collection. Well, it's time to start assembling. For this I will need small screws. I'm gonna start by installing the power supply board. There is a small gap designed to hold it in position. Next, power cable socket. Next up will be ESP chip. I like how it looks in the very front. Our complex scheme comes to the stage. Firstly, I will place amplifiers. Next, the step-up converter. It doesn't have any holes for the screws, and I made some gaps so it could just slide in. It's time to install the speakers. But first, I want to connect the wires to the chip. Great, now let's place them. Bigger screws are needed here. Done. Before I install the second speaker, I want to sort out the wires because it will be hard to get to this place later. Here is our 5-volt power supply for the chip. I will use this connector as is, and just plug it to the pins directly. Now we can install second speaker. The second screw is located in such a narrow place that my screwdriver does not fit there. Well, if I can't reach it with a screwdriver, I still have an Allen key. Now that all the main components are in place, we need to make some space for the battery. Fits perfectly. Now, when everything installed, we have one last piece left. The power button. But since I am using connectors, we can already connect power to the board now. First, I will connect the battery directly. The indicator lights up, the device is working. Now, let's connect it through the charging board. This connection now allows to charge the battery, but the device will still always be online. Let's finally add a button to the chain. I attached two connectors to it, input and output, so it can be simply inserted between elements. The ground line is connected directly, and the LED ground contact is also connected to it. Power line is open, it connected to opposite button contacts. The pressed button will close circuit, providing power to device, and at the same time to the LED lamp. Let's install it. Done. Our device is completely ready to work. We still have these yellow wires sticking out, which do not affect its operation in any way. The reason I have not connected them yet is that I am not sure whether the difference will be heard at such a close distance, and I can only test this on a fully assembled device. Let's press the power button for the first time. Oh yeah! The lights are on, the board is working, which means everything is ready for the first music playback. I am very happy with the result. Everything fell into place and I did not encounter any problems during assembly. It seems that the hours spent thinking and modeling were worth it. Let's check the sound. I turn on the device, all the indicators are on, which means it should be available for connection. After I turned on Bluetooth on my phone, you can see that the speaker immediately tries to pair, since I have already connected to it before. There it is, displayed among other devices and ready to connect. Done, let's play something. Not bad. I am pleased with the result, and it's finally time to try the stereo. So we have two wires connected to the SD pins of the amplifiers. The amplifier reads the incoming voltage to determine which side to play. Now, since they are not connected to anything, the voltage in them floats around 0. If we want the speaker to play only the right channel, it should be between 0.77 and 1.4. And for the left channel, any above 1.4. For now, they both play a mono sound. We can provide voltage for left channel already, but still need to find one for the right. And we can achieve it with the resistors. And again, I will use the breadboard. We have a 5-volt power supply, but on the other side, there is also 3.3 volt that we can use as a source. So we have two identical 10,000 ohms resistors in chain. Let's turn power on and measure it. If I touch the contacts on the edges, you can see our 3.3 volts. But here's what happens if I take the power input from between two resistors. Voltage divided by 2. And to get 1 volt, we need to divide not by 2 but by 3. So we need to add one more resistor on one side. Measuring again. Done. We divided our incoming 3.3 volts by 3, and got 1.1 volts, which is suitable for us. Now let's connect the amplifiers. Everything is set up for stereo playback, but there is no way you can hear the difference watching the video, so just trust me, it works. So I played with some tests and different music to see if I needed it or not. And I can say that even though the speakers are close to each other, there is still a difference between the mono mix and the stereo, and I like the second more. It was very easy to apply. I simply cut off the excess length and assembled a similar circuit directly on the wires, adding a connector on one side. And this is the result. All the internals are completely ready. By the way, it has a pleasant weight. All that remains is to cover it with a case. As you can see, there are also supports on the edges because they are rounded. The edges are ribbed and rough from the supports. I'll sand them down a bit. Now the edges are smooth, but in the corners you can see the abrasions from the sandpaper. I am completely okay with this, since I will use it often, and the scratches that will appear during use will not be noticeable. It looks a bit like jeans. Let's place it. There are 4 small holes for mounting the case. Fits perfectly. Whole thing feels very solid and nice to the touch. And here comes the very last part. Front grills. I'm satisfied. I think it turned out pretty good. What do you think about this? It was a long and hopefully informative video, and if you enjoyed, please give it a like so I know this type of content is interesting. I want to thank you for watching, and say, see you on the next project.